Thank you.
This class isn't very full. If you want to sit at a table, you can. Yeah.
Yeah.
How it's oh, that's like quite a bit. Right.
Wednesdays.
No.
Oh. It would be it's like entropy.
And this is like, what do you do after this step, you know?
Yeah.
Like,
And when she started a problem, she like tried to go through problems for all of us. And she just like would ask us, so how should we proceed? Someone would answer and then she just go, nope. I think she did it again.
Yes.
But like, we need some help here.
They do teach you members them.
No, I don't know. It is what it is. Just as long as it's it's fair. Yeah, something like that.
Yeah.
Oh, dude, no.
That's an old memory lawyer. Oh my goodness.
I think I'm getting emailed Rebecca about assignment 4.
I did, yeah.
You did? You're back. Did you hear back?
No, it's control.
Okay, because if she doesn't,
Problems. After we talk about the fact.
well, no. Yeah. I heard him kind of mention
Yeah.
that it wasn't up yet. I don't know. Okay, I will email Danielle on the back. Or what are they?
That's my favorite colors. Yeah.
We literally learn like bare bones, like this is the stuff we did in pharma, pretty much. Just plug in the function, take the first derivative, and the second derivative, it's not equal to zero.
All right, so I think we'll get started. Hope everyone's doing well. So what I want to do today is I want to work with this binomial distribution that we developed last time. And so at first I want to see if we could calculate some properties of the binomial distribution. In particular, we'll try to calculate the mean, and then we'll at least maybe set up the calculation of the standard deviation of the binomial distribution, and then that calculation will probably be left as a homework assignment. So I haven't posted a second assignment, but I'm hoping that I'll be able to get that posted maybe by Friday or maybe on the weekend sometime, but it'll probably be like a binomial distribution kind of assignment. So probably after today's class, we'll have covered, you know, most of what you would need for that assignment. So the binomial distribution, what is it? We are going to imagine doing some kind of measurement where you can only have one of a small number of possible outcomes, and we're going to identify like a particular outcome as a success. So like if you're drawing a card, maybe drawing a heart would be a success or something like that. And so what we're going to do is we're going to do the probability of getting X successful outcomes when we have N trials, where the probability of any given or any individual trial being successful is this little p. And then so we had to do this, you know, I think they call it combinatorics, right? These factorial calculations. So we derive this prefactor, this n choose x, and then remember we said, okay, if we're going to have x successful events, what we're really asking is what is the probability of getting success x times, followed by failure, and minus x times. And so to get those probabilities, you do products. So you take the product of p x times and the product of 1 minus p n minus x times. And then this prefactor calculates all of the different combinations of having X successful trials out of N total trials. So instead of having all the successes at the beginning and all the failures at the end, you could have any mixture of those things. Okay, and so what we want to do then is we want to now calculate the mean and the standard deviation. And I have a error here. This expression is for the square of the standard deviation. And so we're going to do this calculation, and we're going to leave this one for you, but the procedure will kind of use some of the techniques that we use for calculating the mean. So follow along with this calculation, because you're going to have to reproduce, you know, something similar in your next assignment. All right, so we're going to try to do this sum where we sum over all of the possible outcomes. And so we have to think about what are the possible outcomes. So to find the mean of the binomial distribution, we have to sum over all possible outcomes when we have N trials. Okay, but this is not that complicated to think about, because if we're going to have a experiment where we have success or not, the possible outcomes for n trials is, well, one outcome is they all fail. There's no successful events. So let's just list the possible outcomes. Here we'll call it possible outcomes. Well, a possible outcome is x equals 0, so there's no successes in n trials. Then we could have one success. So one success. And then you probably already see where this is going. We could have a possible outcome is x equals 2. So we have 2 successes out of our n trials. And this is just going to keep going. And we could go all the way up to, you know, we do n trials of our experiment and they all come out successful. Like we flip a coin n times and it's heads every single time. That's possible, right? So there's n successes. Okay. Well, then if we were to write down this mean, it's going to be the sum over all possible outcomes, and we just listed them, and it could be x equals 0 all the way up to x equals n. So we sum over all possible outcomes. And then our mean calculation is inside the sum. We just take x and multiply it by whatever the appropriate probability distribution is. For us, we're going to use the binomial distribution. So we would just take x times the binomial probability distribution. And so this is just going to have that n choose x, the factorial prefactor, and then p to the power x times 1 minus p to the power 1 minus p to the power of n minus x. Okay, so let's write that down. Mu is going to be the sum of x equals 0 to n of x times pb. Sorry, we already wrote that part. Let's put in the actual factorials now. N factorial over x factorial, n minus x factorial. And then we have p to the power x and 1 minus p to the n minus x. Okay, and so we're going to try to tackle this calculation. There's going to be a number of steps. None of the steps are particularly difficult. There's just a sequence of them to go through. Before we do the calculation, I want to see if we could figure out what the answer must be. So think of it this way. If I roll a single die n times, how many times am I going to get a 3? 1/6 of the time. So how many times? It would be n divided by 6, right? But also 1/6 is just the probability that any single trial is going to be a 3. And so that's exactly what this p is. P is the probability of success. So another way of saying that, if I roll a die n times, the average number of times I'll get a 3 is going to be p times n. We could do another one, like if I draw a card, you know, if I draw a card from a full deck 100 times, what's the, well, let's see. Yeah, okay. How many times am I going to get the ace of hearts? Well, it's 1/52 is the probability of getting the ace of hearts. And so I just take the number of trials, multiply it by the probability. So what we're expecting to get is just n times p. So we're expecting to find that mu is equal to n times p. So this is the number of trials, and this is the probability of success for any single trial. Okay, and so you know, it's not obvious looking at this that this complicated sum is going to evaluate to such a simple result, but let's see how we can do it. So the first thing that we're going to do is I'm going to note that we have this x divided by x factorial. So we have x over x factorial, but x factorial is just x times x minus 1 times x minus 2 and so on. And so what we could do is we could cancel this x with the factor of x that's in the denominator inside the factorial of the denominator. And this would have to be the same thing as x minus 1 factorial. Okay, so we could just write this x over x factorial as 1 over x minus 1 factorial. And that's the first thing we'll do. So mu is going to be the sum of x equals 0 to n of n factorial. Let's see. Well, oh, okay. We are going to do that. I'm going to do one step first. Okay. So the first thing I'm going to do is I'm going to write the sum as a sum of x equals 1 to n. And the reason I can do that is because if I put in x equals 0, I'm going to get 0 times all this factorial stuff, and it's just going to be a 0. You might be worried about the x factorial in the denominator. What is 0 factorial? 1. Okay, so we'll note this, and then we'll also, at the same time, let's write the sum of x equals 0 to n of x times some stuff as 0 times some stuff plus x equals 1 to n times x times some stuff. So I'm just pulling out the first term from the sum, and I'm doing that because the first term is just going to vanish completely. And so this one would go to 0. Okay. So if we do that, then mu is going to be the sum of n equals 1, x equals 1 to n. X equals 1 to n. Okay, and then it's going to be x, and we'll have our n factorial, and then I'll write x factorial is x times x minus 1 factorial, and then we'd have n minus x factorial, that stays the same. P to the x stays the same. 1 minus p to the n minus x stays the same. And here we can now cancel these 1 factors, the x in the numerator and denominator. Okay. So now I have this x minus 1. What I'm going to try to do is I'm going to try to find ways to make this an x minus 1 and this an n minus 1. And we're eventually going to do a substitution to get rid of those minus 1s. So we'll do a couple things. We'll write p to the x as p times p to the x minus 1. Okay, that's the same thing. And we'll write n factorial as n times n minus 1 factorial. Okay, so if we do those things, then our our mean is going to be the sum of x equals 1 to n. Okay, we're going to get this factor of n, and we're going to get a factor of p. So I'm going to put the np here. And then we'll have n minus 1 factorial divided by, the denominator doesn't change. We'll have our x minus 1 factorial, and then our n minus x factorial. And now we'll have p to the x minus 1, and we'll have 1 minus p to the n minus x. Okay. So you can start to see that what we guessed is that our final answer is going to be this n times p factor. So somehow it must be that all of this other stuff inside the sum is going to evaluate to 1. And so our remaining task is to see if we can show that everything inside the sum except for the n times p is going to evaluate to 1. Now, n times p doesn't depend on x. X is our summation variable. So if this was like an integral, we'd be like integrating over x, and as long as we had factors that were independent of x, we could take them outside the integral. We could do the same thing for a sum. We're summing over the variable x, and in p are constants, they come outside the sum. And so we're going to take this over here. And so now mu is going to be np times x, the sum of x equals 1 to n, and I'll just rewrite everything here. I won't make any changes yet. N minus x factorial, p to the x minus 1, 1 minus p to the n minus x. All right. And so now we're just going to try to make some manipulations of the sum. What we're actually going to try to do is we're going to try to show that this thing is another binomial distribution. And then if we sum over all of the possibilities of the binomial probability distribution, that probability will have to sum to 1. That's where we're headed with this. So let's make a substitution. Does anybody have any ideas of what kind of substitution might be a good one to make? Binomial distribution doesn't have an x minus 1 factorial, and the sum starts not from x equals 1, but from x equals 0. So what if we made a substitution for this x minus 1? Okay, that's what we're going to try to do. We're going to try to make the substitution y is equal to x minus 1. All right, and so that means wherever I see an x minus 1, I'll put in a y. Wherever I see an x, I'll have to put in y plus 1. So this implies, of course, that x is equal to y plus 1. And then I also have to worry about my limits of the sum. And so the sum limits, let's see, when x is equal to 1, which is our lower limit, y is going to be x minus 1, so it'll be 1 minus 1 is 0. So this will reset the lower limit of my sum, but it's going to do something also to the upper limit. When x equals n, let's see, y will be x, so it'll be n minus 1. Okay, so let's stick those things in there. So we make the substitution, mu is equal to np, that doesn't change. Now, our sum is going to be over y now, so y is going to be from 0 to n minus 1. N minus 1. So, okay, so that's just going to stay the same, n minus 1 factorial. And then we have x minus 1 factorial in the denominator. That's going to be y. And then we have n minus x. But x, in terms of y, is y plus 1. So it's going to be y plus 1. And that's a factorial. Okay, and then we have p to the x minus 1, but that's just a y. And then we have 1 minus p, n minus x. So it's n minus y plus 1. Okay, so some of what we wanted to do kind of made a bit of sense here. We have now this y factorial, the lower limit is right, but we still have some problems over here with like some extra plus ones are hanging around. So what we're gonna do is, let's see, we're going to write this as NP y equals 0 to n minus 1. I can't do anything with the n minus 1 factorial yet, but then we have a y factorial. And then I'm just going to make this n look like an n minus 1. I'm going to try to match this numerator. So I have n minus 1 and then minus y. So it'll be n minus 1 minus y factorial. And then we'll do the same thing over here. So this will be p to the y, that doesn't change, 1 minus p. And let's see, we'll have n minus 1 minus y. Okay. So now we're getting pretty close to where we want to be. We're going to make one more substitution, and it's a really simple one. All we're going to do is we're going to say, let's define m to be n minus 1. This sum is over the variable y, so nothing's going to happen to this lower limit. We're just going to redefine n minus 1 to be m. So another substitution. And this time we're going to do m is defined to be n minus 1. Okay, so this is going to be mu. I'm going to leave the np out front alone. And then we have y equals 0. And then wherever we see n minus 1, we'll put an m. So we're going to have an m factorial divided by y factorial times n minus 1 is m. So it's m minus y factorial. P to the y stays the same. 1 minus p. N minus 1 is m minus y. And this thing should now look somewhat familiar. It's written in terms of different variables. Nevertheless, it's exactly mathematically equivalent to our binomial distribution. So this is the binomial distribution for getting y successes out of m trials where the probability of a success in any given trial is little p. So this is just some other probability distribution. And here, I should be careful. I guess I should not include the sum in this little brace here. So this is the probability distribution, and this is summing over all possible outcomes. And so if you sum over all of the outcomes of a probability distribution, all those probabilities must add up to be 1. Okay, and so the sum of y equals 0 to m, p, b, y, and p has to be 1, right? We're summing over all possible outcomes of a probability distribution. Okay, and so then finally we get our final result, and so therefore mu is equal to n times p. And so that's what we guessed at the beginning. In this course, we will end up doing a fair bit of like manipulations of sums of this kind, where we either pull constants outside of the sum or do like these integral like substitutions. And so it's worth kind of getting comfortable with these sorts of manipulations. All right. Is there any questions about that? No. All right, so what I'm going to do is I'm going to write down the results for the standard deviation. And so in your assignment, you will work this one out. All right, so if we were to calculate the standard deviation, we would do this kind of calculation. Sigma squared would be the sum over all possible outcomes, and then it's x minus mu squared times the probability distribution. Okay, the result, if you do this calculation, is going to be NP times 1 minus P. And so again, it's a complicated looking sum to start, like especially when you write this probability distribution in terms of like the factorials out front. But it boils down to a pretty simple result. Okay, and so you will show this in homework too. All right. So what I want to do is I want to do an example where we actually work with a probability distribution, a binomial distribution in particular. And so we're going to talk about the one-dimensional random walk. All right, and the way people often think about a random walk is let's imagine, okay, you go out for the night, you get blasted at a pub, okay, and then you got to get home. And so the random walk is there's some probability that you're going to stumble left, and there's some probability that you're going to stumble to the right. And we want to figure out how long would it take you to make it home if you have to take, say, I don't know, 100 steps to the right or something like that. Okay, and so this is also related to the experiments that we have the Brownian motion. In Brownian motion, you look at these little spheres, polystyrene or styrofoam spheres that are 1 micron in size, suspended in water. And you look at them into the microscope, and then you can see them moving around randomly in 2 dimensions. And so the Brownian motion experiment is like an example of a 2-dimensional random walk. We're gonna tackle the 1D problem right now. Okay, so a drunk starts at a stop sign, maybe just outside the pub or whatever. And this person, they have a probability P of taking a step to the right, and a probability Q is equal to 1 minus P of taking a step to the left. Okay, so after n steps of size, say delta x, we're going to assume that every time they kind of stumble one direction or the next, their step size is going to be the same, or they have some average step size, and we'll call that delta x. And so the question is, what is the average distance from the sign, and what is the standard deviation? All right, before we work out some of the mathematical details, if the probability of a step left or right is like 1/2 and 1/2, after a large number of steps, what's the displacement going to be? 0, right? Because I've taken, in general, just as many steps to the left and as as I have to the right. And so I might, if I'm at the stop sign, you know, there are times when I could be to the left of the stop sign. But then if I wait long enough, I'll get back, and sometimes I'll be to the right, but if I wait long enough, I'll end up back at the stop sign. So if the probability of stepping left and right is equal, you don't make any progress away from the stop sign. But you sample part of the space, and the part of the space that you sample is characterized by the standard deviation. And so what the drunk might do is they take enough steps that eventually they're far enough away from the stop sign that they're in front of their house, but they don't realize it. And they keep taking steps, and then they end up back at the stop sign after long enough. Okay. All right, so let's see what happens. Okay, so the average number of steps to the right, we'll call it mu sub r, is just the total number of steps taken times the probability to step right. And so that means the average displacement to the right is going to be, well, it'll be the number of steps that I've taken to the right times, well, this delta x, wouldn't it? So it would be NP times delta x, right? Take the number of steps that I've taken to the right, multiply it by the step size. Okay, so then we could do the same thing for the average number of steps to the left. So mu left is going to be the total number of steps times the probability of stepping to the left. So it's NQ, or if we write Q as 1 minus P, it's N times 1 minus P. And then the same thing, the displacement to the left, we just take this and multiply it by delta x, and I'll put a negative sign in front of it. So those are going to be displacements to the left. So the average displacement to the left is going to be N1 minus P delta x, and then we'll put a minus sign in here. Okay, so then our net displacement, well, we just take how much we move to the right and add it to how much we move to the left, or subtract it from that. And so we would end up with, let's see, NP delta x to the right minus N1 minus P delta x to the left. And let's see, are there any kind of simplifications? So we would have NP delta x minus N delta x plus NP delta x. And in fact, there are no cancellations, but we have two similar terms, and all of the terms have an N delta x in it. So we could factor that out. And so it would be equal to N delta x. And then what's left over? It's 2p minus 1. All right. So that's our net displacement. And let's see, we made a prediction at the beginning. If we said the probability of stepping right is exactly 1/2, then we get 2 times 1/2 is 1, minus 1 is 0. So this net displacement on average is 0. And that's consistent with what we expected, right? You could test other extreme cases too, right? Let's say that you come out of the pub and you're at the stop sign, but you're on like this really steep slope or something like that. And so you're only going to step down the hill. And so your probability of stepping to the right is, let's say it's 0. Then your displacement would be minus N delta x. It's all your steps would be to the left. Or if the probability of stepping to the right was 1, you'd get 2 minus 1 is 1, so it's plus N delta x. So all of those kind of simple cases make sense. So if P equals 1/2, then the net displacement is 0 as expected. Okay. So sigma squared would be NP1 minus P. That's what you're going to calculate in your assignments. And so what would happen is this would characterize the spread in the number of steps to the right. And so this spread in the number of steps to the right is going to grow as n increases. And so if we were to take the square root, so we're actually calculating the standard deviation instead of the square of the standard deviation, we would see that that spread increases as the square root of n. So the spread in the number of steps to the right increases as square root of n. So if we're thinking about our drum, what we could say is, all right, maybe the probability of stepping left and right is equal, and so our net displacement on average is 0. But if I just keep taking steps, sigma is going to characterize like the size of the space I sample. And if I take enough steps, if I take n big enough, then I will eventually sample enough of the space that at some point I'm going to appear in front of my house. And if I happen to look up, I'll be like, oh, that's where I'm going. So even though you're not making any net displacement on average, you could still sample enough space that you run into your house by accident. Okay, good. So what I want to do is I want to see what this, we haven't actually ever looked at a binomial distribution. And so I want to put in some numbers and see what these binomial distributions look like. How are we doing time-wise? Oh, we're not bad. Okay. So if P equals Q equals 1/2 and N equals 10, we're just going to calculate some of these probabilities. So what I'll have here is column X, and we said all of the possibilities for X, it could be anything from 0 to N. So 3, 4, 5, 6, and then we'll jump down to 10. All right, and here we're going to put in our binomial distribution probability, where we're going to have the probability of X successes in 10 trials, where probability of success in any trial is 1/2. All right, and let's just write down here that binomial distribution once again. So it's n factorial, x factorial, n minus x factorial, p to the x, 1 minus p to the n minus x, right? So some of these we could probably work out in our head. If what's the probability of taking no steps to the right, let's say? So what you would have to do, you have to step to the left and then step to the left and step to the left. So what's the probability of taking 1 step to the left?
1/2.
1/2. What's the probability of taking a step to the left and then a step to the left again? Yeah, 1/2 times 1/2, a quarter. So the probability of taking 3 steps to the left in a row is 1/2 times 1/2 times 1/2. So it's 1/2 to the power n, right? So if all of my steps are going to be exactly to the left, the probability of that occurring is 1/2 to the power 10. Okay, and I think if you punch that into your calculator, it's 10 times 10 to the minus 4, essentially, or 1 times 10 to the minus 3. So the chances of that happening are about 1 in 1,000. So if you took 10 steps, the probability of getting them all to the left would be 1 in 1,000 times. And so that's exactly the same for flipping a coin. Flip a coin 10 times, what's the probability that you're going to get all heads? Well, it's about 1 in 1,000. Okay, so then next what we could do is say, all right, if x equals 1, then if you put the numbers in, you're going to get 9.8 again, but it'll be 10 times 10 to the minus 3, or times 10 to the minus 3. So it's 10 times higher, the probability increased by a factor of 10. So about 1 in 100 times, your 9 of your 10 steps would be in the same direction. And so then we would have 4.4 times 10 to the minus 2. Then for 3, you'd get 0.12. 4 is 0.21. 5 is 0.25. 6 is 0.21. And 10, what would 10 have to be?
The same as 0.
Yeah, exactly. Whether I take all my steps to the left or all my steps to the right, if probability of P and Q are both 1/2, that has to be the same. And you could actually see in these numbers that this is a symmetric distribution, right? So if we go up from x equals 5, it looks the same as if we go down from x equals 5. So this distribution is symmetric when P is equal to Q is equal to 1/2. All right, so what I'm going to do is I'm going to plot this thing and let's see what it looks like. So this is our probability distribution and here's X. The mean for this case, mu, would be equal to NP, and so that would be 5 if we had n steps and P is 1/2. And then sigma was, let's see, sigma squared was equal to, what was it? It was NP 1 minus P. And so that's going to be 10 times 1/2 times 1/2. And so it's 10 over 4. It's 5/2. So sigma is the square root of 5/2. Okay, so let's try to plot this. And so here is 5, x equals 5. That's where our probability distribution is a maximum. And so that is equal to 1/4. And so we'll call this a quarter over here. Okay, and then we go to either 4 or 6, and we get to 0.21. And so we'd say 4 and 6. And I don't know where 0.21 is. It's something like this and something like this. Okay, and then we go to 3 or 7, and it would be 0.12. So we have to kind of almost exactly half. So if this is 3 and this is 7, so it's maybe a little under half of the height. And so it's going to sit here and here. And then we'd have 2 and 8. And now that is 0.044. And so now we're getting pretty low. So we're down here and here. And then, I didn't do this perfectly, but it'd be something like this. So here's X. Okay, and then our probability is going to look something like this. And we have our mean, mu sits here, and our standard deviation is something, I don't know, what's 2.5? What's the square root of 2.5? I don't know, it's like square root of 2.5. Square root of 2 is 0.14. So it's something like 0.15. Sorry, square root of 2 is 1.4. So it's something around 1.5-ish. And so sigma might be something along these lines here. Okay, good. So that doesn't look so different than like our Gaussian distribution. It's not the same shape, but it's not different in our, it's similar in that it's a symmetric distribution and the mean sits right at the peak. I want to show you that that's not always the case. We considered the special case where probability of stepping left and right is equal. Yes.
Just with the sigma, do we generally just ignore the negative? Like,
Oh, because it has two roots.
okay.
Yeah, there would, so there's another sigma here, right? Is that what you're saying?
Well, just like sigma squared is equal to negative 5/2.
Why is it equal to negative
So
5?
probability is 1/2, so 1 minus a half. Never mind.
1 minus a half is plus half. Yeah, all right, good. Okay, so I want to try this case where we have not a symmetric probability distribution. So let's try. Let's see, I want to take P is equal to 1/6 and Q is 1 minus P is 5/6. Sorry, I've got something in my throat. I don't know what's going on. We'll see if I can power through. X 0, 1, 2, 3, 4, 5, and I'm just going to stop there and go to 10. So binomial distribution for X out of 10 trials when the probability of success is 1/6. So now we're much more likely to step to the left than the right. Maybe the drunk is on a slope or it's a windy day or something like that. Okay, so what's the probability that all of the steps are to the left? What would it have to be? Before it was 1/2 to the power 10, what would it be in this case? 5/6 to the power 10, right? Probability of one step to the left is 5/6, and then we have to take 10 of them in a row. And this comes out to be a pretty big number, actually, 0.16. So 16% of the time, if you took 10 steps, they would all be to the left in this case. And we could do 10, sorry, 10. And so that would be 1/6 to the power 10. And that comes out to be 1.6 times 10 to the minus 8. So it's like 1 in 100 million times that may happen when the probability of stepping to the right is 1/6. And so it's kind of neat, right? Like 1/6 is not that small, and 10 trials is not that many trials, but these numbers conspire to say that, you know, it's almost impossible that all your steps would be to the right in this case. So it's kind of interesting, or it's nice to see how these numbers can really blow up or shrink down so quickly. All right, and then if you just went and filled in these other cases, what we're going to find are the following results. And you can see immediately, even before we plot this, that this is not a symmetric distribution. In fact, the peak is close to x equals 1, and then it falls off kind of quickly after that. Okay, so we'll plot this distribution, and that will probably be basically what we have time for. So here is x. Here's PB. And then let's see, 0.16. We have to find 0.32. So let me put 0 here. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so here's 1 and here's 10. Okay, 1 happened at 0.32, and so we're gonna have to call this 0.32, and then 0 happened at 0.16, and so that's exactly half that height. And then 0.29 is up here, 0.16, oh, so that's got a match over here. And then we get down to like 0.05, 0.01, and then basically so small that it's just sitting right at 0 essentially. And so our distribution would look something like this. And so clearly it's asymmetric. Let's add the mean onto this plot. Mu is going to be n times p, which is 10/6. And so that's what, 5/3. What's 5/3? That's 1 2/3, so it's 1.67, I think. 1.67 probably. And so where does that sit? That sits right about here. And you can see that that's not quite at the peak of our distribution. And so here is mu sits somewhere around here. And it's not at the peak because this thing gets cut off at 0. And so, you know, there's higher probability on this side, but there's a large range of possibilities on this side, and that skews the mean to be a little bit off of the peak of the distribution. Yeah.
Is it the same shape as the other graph, just shifted?
No, no. So this is not a symmetric distribution. So like if I overlaid this on the other one, they wouldn't overlap.
And
Yeah.
if you like look for 0?
No,
It would be
no, it wouldn't be. Yeah. So, and here the mean is to the right of the peak in the distribution. And let's just quickly, let's figure out sigma. Sigma squared is what? NP1 minus P. And so that's 10 times 1/6 times 5/6. So what is that? It's 50/36. And then, oh, you know, that works out kind of nice. 50 is close to 49, and 36 is, so 49 is a square, 36 is a square. So if we take the square root, sigma is about 7/6. So it's just over 1. And so sigma is something like this. Okay, good. And so that's where we'll stop. And what we'll do next time is we might think a little bit more about this drunk walking around town and see if we can characterize his motion or her motion in a little more detail. All right, thanks very much.